Um, okay, we're ready to start a new chapter, chapter 2 in our linear algebra book. It's on matrix algebra, and again, some of this may be familiar to you. Actually, let me adjust my drawing program here a little bit. So we'll start out with just an introduction discussing some of the basics of matrix operations. Um, first, let me talk about some notation. We'll have in general, we'll talk about an m by n matrix. That means it has m rows and n columns. So the number of rows is always first. We'll use a capital letter to represent a matrix, typically, A, B, C. And then the elements of the matrix are A11 is the element in the first row, first column. A21 is the second row, the second column. And then finally here, this would be AM1. It has M rows. And then similarly, A21 would be the element in the second column, first row. And then here we have, I'm sorry, let me back up just a second. Went a little too far. That's right. AM1, and then this is the first row, second column, second row, second column. This would be the mth row, second column. And then we have first row, n, second row, n, and finally this would be the mn element. The element in row m and column. And the other way, kind of a shorthand notation, is we'll sometimes use this notation that A is made up of all of these elements, Aij. So, a simple example here at this point, just to put numbers. Here's an arbitrary matrix, 1, 2, 3, 4, 5, 6. So this would be a 2 by 3 matrix, 2 rows, 3 columns. And the A23 element would be the element in the second row, third column, that's 6. So this is the notation we'd use. Sometimes we'll also, this is the notation that's used in MATLAB, for example. A23 would also be equal to 6. Okay, so let's talk about now addition of matrices. In order to add two matrices, they must have the same dimension, have the same number of rows and the same number of columns. But then A plus B is equal to, we just add all the respective elements. Okay. So, for example, A plus B, let's say 1, 2, 3, 4, 5, 6. This is A. B has to have the same number of rows and columns to be compatible for addition. Otherwise, we can't add the two matrices. And then the corresponding result, I just add the corresponding elements. So 3, 6, 3 plus 6 is 9, 4 plus 8 is 12, 5 and 10 is 15, 6 and 12 is 18. So pretty simple. Just add the corresponding elements of the two matrices. Matrix addition is commutative, so A plus B is equal to B plus A, and it's also associative. So A plus the matrix B plus C is equal to the matrix A plus B, then added to C. And then most of these properties follow just from corresponding properties of addition of real numbers. Occasionally we'll have need for a zero matrix. That's the matrix whose elements are all zero, sometimes denoted like this. And then also we can define the negative of a matrix, negative A. It's the negative, we get the negative of a matrix by taking the negative of every element. That allows us then, with the idea of a negative, we can define subtraction as, in terms of addition, A minus B is equal to A plus the negative of B. Okay, let's move on to another fairly simple but important concept. That's scalar multiplication. If we have a scalar K times matrix A, that's equal to the result we get from multiplying every element of A by this constant K. So again, a really simple example. 1, 2, 3, 4, 5, 6. The product will have the same dimension as the matrix. We just multiply every element, in this case, by 2, 6, 8, 10, 12. Okay. So pretty simple. There's some of the basic properties of matrix addition and also scalar multiplication are summarized on page 40 in theorem 2.1.1. Again, most of these, the proofs are simple. They rely on the underlying properties of addition and multiplication of real numbers. Okay, so let's look at an example quickly of similar to one of the homework problems that I'll assign. So we're asked to simplify, say 3a plus b minus 2a plus b. Again, most of the addition and scalar multiplication properties of the matrices are the same as for real numbers. So this quite simply becomes, multiplying the 3 through distributing the 3, then minus, I'll have distributing the 2, 2a plus 2b, okay. And then distributing the minus sign, I'll have 3a plus 3b minus 2a plus 2b, or finally 3a minus 2a is a, and 3b plus, did I do that? This should have been a minus, okay. And then 3b minus 2b is b as well. So just a simple example to illustrate the concepts. Okay, let's move on to the final basic definition in this section. That's the idea of a transpose. The transpose of a matrix is denoted by AT, and then here in the transpose, the elements of the transpose are AJI. Okay, so what this notation means is that we form the transpose of A by swapping the rows and columns. Okay, so A transpose is the matrix whose rows are the columns of A. If A is m by n, then A transpose is n by m. So the dimensions are swapped. So again, just a simple example here. 1, 2, 3, 4, 5, 6. A transpose would be, so the first row becomes the first column. Similarly, the first column becomes the first row. So here I just swap the rows, and this is A transpose. Similarly, you know, the transpose of a column, single column. So we'll call this, I'm treating this as a 3x1 matrix right now, but we'll see that we can represent either a 3x1 matrix or a 1x3 matrix or a 1x(n) matrix as a vector. The transpose of a column vector is a row vector, 1, 2, 3. Okay. Some basic properties of the transpose. The transpose of a transpose is equal to the original matrix, and then the transpose of K times A is equal to K times A transpose. Again, you can prove these quite easily by just writing out A in terms of its elements. And then finally, another property that's useful, the transpose of A plus B is equal to A transpose plus B transpose. So let me work through an example. One of the exercises at the end of this section. So this is exercise 2.1.15a, and we're asked to solve for A here, where we're given this equation, A plus 3 times the matrix 1 minus 1, 0, 1, 2, 4, and all that transpose is equal to 2, 0, 3, 1, 5, 8. And there's a couple different ways that you could work through this. You know, here we got the transpose of a sum, so I could write this as the sum of the transposes. I'm going to use the other property where I'm just going to take the transpose of both sides, and the transpose of a transpose is equal to the original matrix. So here I'll have, on the left-hand side, I'll have A plus 3 times 1 minus 1, 0, 1, 2, 4. And then the transpose of the right-hand side, you get 2, 0, 3, 1, 5, 8. Okay. Lost a parenthesis there. So this is A plus 3 minus 3, 0, 3, 6, 12 is equal to 2, 0, 3, 1, 5, 8. Then now I can solve for A by subtracting this matrix from both sides of the equation. And what I'll get is 2 minus 3 is minus 1. 0 minus a negative 3 is 3. 3 minus 0 is 3. 1 minus 3 is minus 2. 5 minus 6 is minus 1. And 8 minus 12 is negative 4. So this is the corresponding answer to that particular exercise. Okay, I'm going to start section 2 out of chapter 2 on matrix vector multiplication, but I'm going to stop this video here and start that section in another video.